So we're doing how to inspect for moisture intrusion. This course teaches many of the best practices and standards that make a home moisture resistant. Building practices and construction techniques are essential for an inspector to understand. Building components that are defective, incorrectly installed, or simply missing can produce moisture-related problems. Moisture intrusion of a building can cause major structural damage and can threaten the safety of its occupants. Most E&O insurance claims in the inspection industry involve moisture intrusion. Once an inspector knows what properly installed building components look like, then recognizing installation defects becomes easy. Education and training on the best and most recent building practices for controlling moisture are essential for every property inspector. All right. Proper design and construction of homes involves moisture control to prevent deterioration. Recently, this has become more complex as expectations for managing interior moisture has risen. It now includes promoting occupants' comfort, protecting indoor air quality, and preventing mold. Consumers demand better performance of their homes, making total moisture protection a challenging goal. Effective moisture control relies on scientific principles and practical implementation by builders. Property inspectors need to understand moisture control in relation to building standards and practices. This course combines common building standards with property inspection practices. Understanding building methods and techniques is essential for inspectors. Defective or improperly installed components can lead to moisture-related problems. Moisture intrusion can cause structural damage and threaten occupant safety, and if water penetrates a building, it should be allowed to exit. Education on the best building practices is crucial. Moisture-related issues include rain penetration, structural decay, mold growth, high humidity, condensation, wet foundations, and ice dams, all of which we are going to go over in this course. These problems are mostly preventable and manageable. And Benjamin Franklin's advice that an ounce of prevention is worth a pound of cure applies well to avoiding moisture problems in homes. This concept of moisture movement can be complicated to understand. One issue is that we have and use so many different terms, including air barriers, vapor diffusion retarders, vapor permeable and impermeable. Home inspectors often find it challenging to speak with contractors and building officials without using the same terminology. The most important terms a home inspector should understand is that a vapor retarder retards the movement of water by vapor diffusion, and a vapor barrier is a vapor retarder of a certain class, such as a class 1 vapor retarder. Many of these best practices will be found during a home inspection. The lack of a particular best practice for moisture management may not necessarily be a construction defect, potentially leading to moisture intrusion. Caution during an inspection is advised when inspecting for construction practices because a typical home inspection is strictly non-invasive and visual. Building components related to moisture management will usually be hidden, covered, or restricted in some way in a visual-only building inspection. All right, moisture movement. To be able to inspect for moisture intrusion and related problems, an inspector should understand the basics of how moisture can move through a home. Moisture and water vapor move in and out of a house in 3 ways: through air currents, by diffusion through materials, and by heat transfer. Of these 3, air movement accounts for more than 98% of all water vapor movement in building cavities. Air naturally moves from a high pressure area to a lower one by the easiest path possible, generally through any available hole or crack in the building envelope. Moisture transfer by air currents is very fast, in the range of several hundred cubic feet of air per minute. Thus, to control air movement, a house should have any unintended air pass thoroughly and permanently sealed. Moisture flow by vapor diffusion is also governed by the second law of thermodynamics, where moisture will flow because of a concentration and temperature gradient from high to low and from more to less. And that means moisture tends to move in cold climates from inside to out, and in warmer climates move from the outside in. Moisture transfer by air currents happens quickly and carefully, and permanently air sealing any unintended paths for air movement in and out of the house is a very effective moisture control strategy. The other two driving forces, diffusion through materials and heat transfer, are much slower processes. Most common building materials slow moisture diffusion to a large degree, although they never stop it completely. Insulation also helps reduce heat transfer or flow. All right, the laws of physics govern how moisture reacts within various temperature conditions. The study of the properties of moist air is technically referred to as psychrometrics. A psychrometric chart is used by professionals to determine at what temperature and moisture concentration water vapor begins to condense. This is called the dew point. By learning how to determine the dew point, you will better understand how to diagnose moisture problems in a house. You can see here that in cold climates, vapor pressure flows upward through the roof from a warmer, more humid climate to a colder, drier exterior. And in warm climates, vapor diffusion flows downward through the roof from a warmer, more humid climate to a colder, drier interior. Relative humidity refers to the amount of moisture contained in a quantity of air compared to the maximum amount of moisture the air can hold at the same temperature. As air warms, its ability to hold water vapor increases. This capacity decreases as air cools. In addition to air movement, one can also control temperature and moisture content. Since insulation reduces heat transfer or flow, it also moderates the effect of temperature across the building envelope cavity. In most US climates, properly installed vapor diffusion retarders can be used to reduce the amount of moisture transfer. Except in deliberately ventilated spaces such as attics, insulation and vapor diffusion retarders work together to reduce the opportunity for condensation to form in a house's ceilings, walls, and floors. Understanding how water vapor moves can help home inspectors understand what they're observing when inspecting visible vapor diffusion retarders. Most water vapor movement in and through buildings is via air. Air transported moisture in the form of water vapor hitchhiking on the air can leak into or out of buildings. Leaky ductwork, for example, can cause moisture problems by not only increasing the amount of infiltration, but by drawing air in from the humid crawl space or basement area. As this humid air travels through a building, the moisture in it will condense on any surface whose temperature is below the dew point. Water vapor can be a source of damage when it is trapped within a building assembly and cannot dry out. Warm air carries more water vapor than cold air. When warm air touches a cold surface, the water vapor it carries can condense, turning the vapor into its liquid form, where it can cause damage to structural components. All right, here we go. We're getting into the nitty-gritty here, so bear with me. Even without air leaks, small amounts of moisture in the form of water vapor can pass directly through a building's envelope through a process called diffusion. Vapor diffusion from a damp or wet basement into the living space can significantly increase the moisture levels inside a home. Most materials, even glass, are unable to completely stop vapor diffusion. Thus, calling something a vapor barrier is a bit of a wrong label. The current trend in building science is to refer to materials as vapor retarders, meaning that while they retard or slow down the movement of water vapor, they do not completely halt the process. Materials that significantly slow down the vapor diffusion process are said to have a low permeability, or simply low perm, and typical building codes consider a material to be a vapor retarder if it has a perm rating of 1 or less. I want to, before I continue on with my content here, I wanted to point out that I have a really good example of how I didn't understand how glass could not even completely stop vapor diffusion, in that I have a cigar humidor, a desktop humidor, and my wife bought it for me. She was super proud of herself. She got me a really nice one that had a glass top, and I could not manage the humidity on it or inside of it. And so I went to this local cigar shop, and asked them, I was like, what's going on? I was like, this is really high end. It was a gift. I'm really frustrated with not being able to maintain the humidity levels in there. And they asked me, first question he asked me, is it glass or is it plastic? And I said, it was glass. He goes, there's your problem. He said, if we were able to put a plastic like window tint on it, then that would severely slow down the diffusion through the material. So I learned something through that. I was very surprised by his answer. So um, vapor retarders are often applied in a crawl space of a building to prevent ground moisture from evaporating and traveling up into the home. Many building codes require applying such vapor retarding materials under wallboard to prevent vapor diffusion from bringing water into the structural assemblies. In cold climates during the heating season, pressure differential drives the vapor from inside of the building to the outside. I'm seeing the shared screen. Okay. Let's see. In cold climates during the heating season, pressure differential drives the vapor from the inside of the building to the outside. You cannot. Yes, I'm reading I'm going over my presenter notes. You guys won't be seeing what I'm seeing. There's too much content. So it is uh, in relation to what's on your screen, what you can't see. So um, you can see the screen that says vapor diffusion and moisture control, correct?
Yeah, we see your share screen, Andy.
Okay, perfect.
Good.
All right, let me get back here. All right. In Minnesota, the vapor barrier is generally installed on the interior face of the wall studs. In warm climates during the cooling season, this vapor drive is from the outside of the building towards the inside. Thus, in Miami, Florida, vapor retarders are often applied on the outside of the buildings. Besides the perm rating of the material, the effectiveness of a vapor retarder is also a function of its surface area. A vapor diffusion retarder that covers 80% of a building is said to be 80% effective. In most North American climates, vapor barriers, or more accurately, vapor diffusion retarders, should be part of a moisture control strategy for a home. A vapor diffusion retarder is a material that reduces the rate at which vapor can move through a material. The older term vapor barrier is still used, even though vapor diffusion retarder is more accurate. It is a myth that installing vapor diffusion retarders is the most important step for controlling moisture in the walls. Vapor retarders only retard moisture due to diffusion, while most moisture enters walls through fluid capillary action or as water vapor through air leaks. Water vapor can also be carried through building components by diffusion, driven by pressure and temperature differences. Vapor diffusion can be impeded by use of a vapor diffusion retarder. Vapor diffusion retarders can help control moisture in basements, ceilings, crawl spaces, floors, slab-on-grade foundations, and walls. Effective moisture control in these areas and throughout a home must also include air sealing gaps in the structure, not just the use of vapor diffusion retarder. However, where and whether a vapor diffusion retarder is needed depends on the climate and the construction of the home. Here's an example or a good diagram showing the differences in class. So the 2015 IRC defines vapor retarders based on their permeability. The ability of a material to retard diffusion of water vapor is measured in units known as perms or permeability. The higher the perm rating, the more easily water vapor can pass through the material. The 2015 IRC describes 3 classes of vapor retarders, including class 1, 2, and 3, which are directly related to their perm ratings. You can see here the examples that we're talking about. All right, class 1 and class 2. So as I stated, I am in Northwest Arkansas, which can anybody see my mouse? See my mouse moving around? Yes, awesome. So you can see in my area, I am in this tiny little corner in Northwest Arkansas. This is Benton County. This is where I live. And I am in climate zone 4A. I am in a mixed humid climate, and it does not require, oddly enough, does not require a vapor retarder if not installed. But if we don't have a vapor retarder in the crawl space, then we must have crawl space vents within 3 feet of the corners of the house, and then well, the calculation is 100 another. I think it's 1 square foot of air per 150 square feet of floor space. Oh yeah, 3 and 1 for every. Okay, I didn't realize I had that in there, but it's a 1 for every 150 square feet of floor space if there is not a vapor retarder on the crawl space floor. Class 1 vapor retarders include glass, sheet metal, unperforated aluminum foil, polyethylene sheet, and a rubber membrane. Some builders refer to Class 1 vapor retarders as vapor barriers, but the code no longer uses the term vapor barrier. And Class 2 vapor retarders greater than 0.1 perm and less than or equal to 1 perm include unfaced, expanded, or extruded polystyrene, or 30-pound asphalt-coated paper, and plywood, bitumen-coated, and I don't know how that got cut off on the bottom there. So bitumen-coated paper, I guess. So depending on where you're at on this map will dictate, whether or not you're going to be required to have a vapor retarder for your crawl spaces, and where it's going to be placed, either inside or outside your home, or the home you're inspecting. Because of a change in the 2009 IRC, Class 3 vapor retarders, such as latex paint, are now permitted in several climate zones that you can see on the table there. Let's see, when the wall is constructed in a way that allows drying through the use of vented cladding, examples like brick or lap siding with an airspace behind it, or reduces the potential for condensation by use of insulating rigid foam sheathing. The U.S. Department of Energy's Building America scientists caution that the recommendation to install a vapor barrier on the warm in winter side of the wall assemblies is difficult to apply in mixed climates or climates that are air conditioned in the summer. They recommend that walls should be allowed to dry to the inside, the outside, or both sides, and they don't recommend the use of Class 1 vapor retarders in any but the coldest climates. If you're interested in that website, you can go to www.energy.gov, and you'll find navigate through there to buildings and Building America. Vapor diffusion retarders are typically available as membranes or coatings. Membranes are generally thin, flexible materials, but also include thicker sheet materials, sometimes called structural vapor diffusion retarders. Materials such as rigid foam insulation, reinforced plastics, aluminum, and stainless steel are relatively resistant to water vapor diffusion. These types of vapor diffusion retarders are usually mechanically fastened and sealed at the joints. In mild climates, materials such as painted wallboard and plaster wall coatings may be enough to impede moisture diffusion. In more extreme climates, higher perm vapor diffusion retarders are advisable for new construction. They perform best when installed closest to the warm side of a structural assembly, toward the interior of the building in cold climates and the exterior in hot, wet climates. A vapor diffusion retarder installation should be continuous and as close to perfect as possible. This is especially important in very cold climates and very hot, humid climates. Care should be taken to completely seal any tears, openings, and punctures that may occur during construction. And as we all know, if you've ever done a phase inspection and you see what the walls, the structural sheathing on the exterior looks like before they put the siding on, we know that that does not happen, which makes it more important for us during a home inspection to pay close attention to those penetration areas. Except for extensive remodeling projects, it's difficult to add materials such as sheet plastic as a vapor diffusion retarder to an existing home. Obtaining an energy audit and thoroughly sealing any leaks it reveals is a very effective strategy for slowing moisture movement in and out of the home. A home may not need a more effective vapor diffusion retarder than the numerous layers of paint on its walls and ceilings unless it's located in an extreme northern climate. Vapor barrier paints can be an effective option for existing homes in colder climates. The perm rating of the paint should be indicated on the label. Glossy paints are generally more effective vapor diffusion retarders than flat paints, and acrylic paints are generally better than latex paints. Okay, all appropriate surfaces should be covered or moist air within the cavity may condense, which could lead to dampened insulation. The thermal resistance of wet insulation is dramatically decreased, and prolonged wet conditions will encourage mold growth and wood rot. An air barrier vapor diffusion retarder attempts to accomplish a water vapor diffusion and air movement control with one material. This type of material is most appropriate for southern climates, where keeping humid outdoor air from entering the building cavities is critical during the cooling season. In many cases, air barrier and vapor diffusion retarders consist of one or more of the following materials: polyethylene plastic sheets, builder's foil, foam board insulation, and other exterior sheetings. Moisture is a common cause of building degradation. In fact, much of what we know about applied building science today originates from early work investigating moisture impact on the buildings. While the severity of moisture problems varies greatly depending on climate, few regions in North America are free from concerns about moisture in buildings. Moisture can attack a building's durability on many fronts, from wet crawl spaces to leaking roofs. Moisture-rich air can even become trapped in building structural assemblies, possibly leading to mold growth, rot, or insect infestation. Entire industries have developed that specialize in combating these various moisture problems. At the end of this class, I have some great pictures that will be able to show you things that we found in the field and how the exterior cold air in my area, Northwest Arkansas, how exterior cold air came through the bottom of the sill plate, came into contact with the interior floor trim, made it very cold, and then you had the hot, humid air inside the home from the kids showering and cooking, and those two contacted, and then the whole baseboard of this living room house had condensation all over it. Nobody could figure out why or where it came from. Everybody thought that there was a leak, but it turns out it was just condensation from the dew point on the trim because of the lack of a sill gasket. Because sill gaskets in my area are not required, interestingly enough. So, all right. Now getting to the inspecting portion of, now that we have some information, some details, we're going to get into how to inspect for moisture intrusion. So the following sections refer to the building practices that prevent moisture problems, which may be consistent with minimum building codes and standards. There are practices that go beyond code requirements, best practices or installation instructions, that type of stuff. Home inspectors are typically not required to inspect for code compliance. However, knowledge and understanding of building codes and standards are sometimes necessary in order to inspect for building practices that are causing moisture-related problems, such as missing kickout flashings that should be installed according to the Model US building standards. In my area, kickout flashings causes by far the most amount of damage, or missing kickout flashings causes the most amount of damage to homes in my area when it comes to moisture intrusion. Commenting upon codes and standards is beyond the scope of a typical inspection. Home inspectors are not code inspectors, but home inspectors do use building codes and industry standards as reference sources. Roof coverings provide a first line of defense against the elements. They also tend to be the most exposed components of a building's exterior envelope. Therefore, roof coverings should be selected, detailed, and installed to provide durable resistance to water penetration. Because more than 75% of all homes in the US use composition roof shingles, we're going to focus on that type of roof covering in this section. Home inspectors should know the importance of minimum roof slopes for various roof coverings. Underlayment installations are not readily visible except for the possibility at the eave and rake by gently lifting up the edge of the shingle, but do not break the connection, the tack strip connection, and do not tear the shingles or damage the shingles in any way. If you're going to try and identify the configuration of the underlayment. So IRC 903.1 in general says roof decks shall be covered with approved roof coverings secured to the building or structure. Roof assemblies shall be designed and installed in accordance with this code and the approved manufacturer's installation instructions, such that the roof assembly shall serve to protect the building or the structure. Building codes don't address many of the details required for complete and proper installation of the many available roofing products. Therefore, the statement regarding in accordance with manufacturer's installation instructions should not be taken lightly. Industry standard installation guidelines are also important resources. Home inspectors are not usually expected to determine conformance with the manufacturer's installation recommendations or compliance with local building codes and regulations. However, there are many standards and building practices that should be checked during a typical home inspection. For example, most, if not all, asphalt composition shingle manufacturers will void the warranty of the shingles if they are installed on a sloped roof of less than 212 roof slope. We'll go over determining what the roof slope is here shortly. All right. So understanding minimum roof slope and check the underlayment. So steep slope roof systems are defined by the National Roofing Contractors Association, the NRCA, as systems designed for installation on slopes greater than 312 or 14 degrees. Steep slope roofs are water shedding, but not waterproof. Therefore, roof slope is limited in accordance with the table that you see here. To prevent water leaks, these roof systems rely on fast drainage, adequate overlapping of elements, and the use of underlayment as a backup layer of protection. For composition shingles and concrete and clay tiles, Figure 1 shows a double underlayment. Yeah, I got the, you see here. Oh, no. Yes, so it's talking about, I'm sorry, I was talking about this this diagram, and it was in speaking, I was referencing this diagram. So you can see here the double underlayment. Shows a double underlayment detail to be used on slopes of less than 412 for use for these two types of roof coverings. For roof slopes between 212, 2 units vertical and 12 units horizontal, which equals a 9.5 degree slope, to a 412, which is 4 units vertical and 12 units horizontal, which equals an 18.5 degree slope. Underlayment should be 2 layers applied in the following manner. A 19-inch strip of underlayment felt should be applied parallel to and starting at the eaves and fastened sufficiently to hold in place. Starting at the eaves, 36-inch wide sheets of underlayment should be applied, overlapping successive sheets at 19 inches and fastened sufficiently to hold in place. Generally, you're not going to see that information, or you're going to see that, but this is just information for you to be aware of. So for roof slopes of 412 and greater, 1 layer of underlayment should be applied in a shingle-like fashion. It should start at the eaves and run parallel to the eaves. It should overlap 2 inches. It should be fastened sufficiently to hold in place. End laps of the underlayment should be offset by at least 6 feet. In areas where there is a history of ice forming along the eaves causing a backup of water, an ice barrier that consists of at least 2 layers of underlayment cemented together or self-adhering polymer modified bitumen sheet shall be used in lieu of normal underlaying, typically referred to as ice and water shield, and extended from the lowest edge of the roof surfaces to a point at least 24 inches inside the exterior wall line of the building. Detached structures without conditioned areas are the exception. By contrast, low slope systems are designed as waterproof roof systems and use a roof covering designed for slopes as low as 1 and from or a quarter to 12, quarter-inch slope, quarter-inch fall by 12 or to 12 inches. While low slope roofs are commonly known as flat roofs, an actual flat roof surface is a design mistake. There should always be some slope, whether it be to the exterior or to an interior drain. Inspectors should report a flat roof that is actually flat as being defective. Optimal slope of a water shedding roof. Considering several factors, a moderate roof slope of from 412 to 712 provides a favorable balance of pros and cons for water shedding systems. For example, lower roof slopes will tend to decrease drainage efficiently, allowing debris to accumulate and increase wind uplift loads on the roof. In addition, as the roof ages or becomes damaged, leaks are likely to be more severe, while very steep roofs will tend to increase drainage efficiency. They increase the building and the roof's exposure to lateral wind loads. Furthermore, water flow velocity will be increased, especially in the valleys, which may cause scour, which is accelerated water and overshooting the gutters. Also, very steep slope roofs are more difficult and less safe to access for construction, maintenance, and replacement. Considerations for low slope roofs and special applications. So you can see here that low slope and special roof covering applications require special attention to material selection. When in doubt, help should be sought from roofing experts or the manufacturer. For example, a waterproof membrane for a balcony or deck surface should be installed. The surface will need to be wear resistant as well as waterproof. In addition, surface must drain a minimum of 1/4 to 12 toward the balcony or deck perimeter or internal drains. Flashing must be carefully detailed at intersections with building walls and membrane penetrations. And in addition, some slope roof applications may require special drainage features such as drain inlets, scuppers, which are they're usually installed off of parapet walls, which are your vertical 90-degree walls where you'll have a chute coming off of the side, and emergency overflow outlets to prevent ponding of water due to extreme rainfall events or sagging of roof members due to snow load. Beware that many of these design requirements may be found in commercial building plumbing code rather than in residential building code. As a result of these design and installation considerations, some membrane roofing manufacturers require their products to be installed by their own network of certified installers. Most homes are designed for a maximum roof covering weight of no more than 5 pounds per square foot. When replacing the roof on an existing home, a structural analysis should be performed if a light roof covering is being replaced by a much heavier roof covering. During a typical home inspection on an existing home, this type of identification will not be possible. However, on a new home being built or on a roof installation project, the rating identification could be accomplished. There is good and bad fastening. The manufacturer's installation instructions should be followed and the fasteners should be properly installed. Appropriate fastener spacing, fasteners installed without damaging material, etc. In general, 6 roofing nails per shingle rather than the standard 4 nails are required for composition shingles in high wind regions. The roofing fasteners should not be overdriven so that the head damages or tears the shingle. To avoid complete loss of shingle strips, which is a major cause of extensive water damage to the contents of a home during wind-driven rain events. Attention to fastening quality is equally important for other roofing materials such as tile and metal. So I have an example. I was called out by a client and their insurance had rejected their claim on their roof. They had wind damage. So he wanted to make sure that the insurance company wasn't just, saying deny, deny, deny. And so he called me out, and sure enough, his roof was 5 years old. The nail pattern was not inside the nail zone. It was above and below. And so the insurance had the right, and so did the manufacturer had the right to reject their claim because the shingles were not installed correctly. So it's incredibly important for our clients that the installation instructions of a product is followed to a T, so that obviously there is not outside forces that can cause damage, but also so that the manufacturer warranty will be maintained. So in this instance, the client couldn't make a warranty claim, even if there was a recall on that shingle because the shingle was not installed correctly. And the insurance would not cover the replacement of the roof after the wind damage because the shingle was not installed correctly. Underlayment. So typically 15-pound tarred felt underlayment provides backup protection against water intrusion only as long as the primary roofing materials remain intact. It is not intended for direct exposure, in the event of loss of the primary roofing system in a severe wind-driven rain event. To enhance protection against water intrusion and damage to the building and contents in severe wind-driven rain climates, a roofing contractor should apply a continuous strip of bituminous adhesive tape to sheathing joints prior to installing the underlayment. This practice provides a level of protection against water intrusion, even in the event of severe wind damage to the primary roofing. For further backup protection, a self-adhering bituminous membrane may be applied to the entire roof. Check the roof sheathing. The roof covering is only as strong as the substrate which it is attached. Roof sheathing in high wind areas should be attached with minimum 8D deformed shank nails or 8D common nails, spaced 6 inches on center at all framing members. Full round head or D head nails should be specified and should not be overdriven into or through the sheathing, as this severely weakens the connection. Composition shingles tested in accordance with UL 2218 and rated as Class 4 may be used for improved hail resistance. Classes range from a low of 1 to a high of 4. In some states, such as Texas, hail damage insurance premiums may be reduced with the use of impact resistance roofing. And in 2004, the Texas Department of Insurance provided an online listing of manufacturers of products that meet the state's roofing discount requirements. If you're interested in that website, you can go to www.helpinsure.com/home/roofing. Another consideration for protecting roofs from hail damage involves re-roofing. Re-roofing over an existing layer of composition shingles, while generally permitted by code, reduces the ability of newer shingles to resist impact damage from hail. Therefore, in hail-prone regions, the insurance industry recommends, and local code may require, that re-roofing should include removal of the existing layers of old composition shingle roofing. Re-roofing is very common in my area. But through that, we tend to see, because when you re-roof, you actually have more give. And so when a hail strikes the roof, it actually creates more damage because it's allowed to deform the shingle much greater than if it were not applied over a second layer of roofing. If you're interested in taking a hail class, InterNACHI has a great hail identification class that I would highly recommend. Minimum roof penetrations. Roof penetrations increase the likelihood of water leaks due to failed gaskets, sealants, and flashing. The number of roof penetrations may be reduced by a variety of technologies and strategies, including AAVs, which are air admittance valves, to reduce or eliminate plumbing vent stack penetrations, consolidation of vent stacks below the roof, like sidewall penetrations, exhaust vent caps routed through walls instead of through the roof, high efficiency combustion appliances, which can be sidewall vented, and electrically powered HVAC equipment and hot water heaters. Water heaters that do not require flue pipes. The more penetrations an inspector finds passing through the roof covering, the greater the potential for moisture intrusion. So you can see here on the left-hand side is a 2015 hail map. More than likely, this has changed because I think it's probably growing, if anything, if not moving. Composition shingles rated for hail resistance or other more resistant roofing materials should be installed for protection from hail damage. Since hail can occur in so many different parts of the country, at least occasionally, the greater the likelihood of hail, the more often enhanced shingles should be seen at inspections. The hail days map shown above is presented as an example and illustrates the mean number of days per year for a hail event that is damaging and or has hail of 2 inches in diameter. When available, maps and indexes found in building codes should be referenced. And then on the right-hand side here, roof concentrations, checking for concentrated and obstructed roof drainage. In modern construction, adding complexity to roof plans is commonly done to improve curb appeal, but adding complexity to the roof drainage system can also create long-term moisture problems. A balance is needed so that roof rainwater flows aren't excessively concentrated or obstructed as shown above. If these conditions cannot be avoided, then affected regions of the roof should be adequately detailed and waterproofed, and guttering should be appropriately designed to channel water off the roof and away from the building. These are critical areas to inspect. So if you can see my mouse over here on the right-hand side, top right diagram, this is where you should have a kick out flashing. And this is a very vulnerable area that should be inspected. If you can get to it from the attic, you should pay special close attention. In addition, and it's hard to see that where these rain drips are coming down, a lot of times, if this roof design is set back, if it's set back further, and the roof design actually came into contact with this sidewall instead of off the front here, then this sidewall intersection is also very vulnerable to water intrusion. The water flow, the velocity coming off of all of these roofs and hitting this sidewall can cause the water to come up and seep into and get past the flashing if it's installed, which it generally is, but it can cause the water to flow back up into the wall system because of the velocity of the water coming off. So this area is incredibly important to investigate for moisture intrusion. Roof flashings. Water penetration is commonly associated with flashing and detailing problems around roof penetrations, eaves, and wall intersections with a lower roof section, as we just discussed in that previous diagram. The following best practices describe flashing details for common applications in residential construction that inspectors should be able to recognize. These conceptual details are intended to help inspectors understand the objective for roof flashing as found in the 2006 IRC. So section 903.2 flashing. Flashings shall be installed in such a manner so as to prevent moisture from entering the wall and roof through joints and copings, through moisture permeable materials, and at intersections with parapet walls and other penetrations through the roof plane. U.S. building codes provide only basic performance concepts for use and detailing of flashing. Therefore, it is imperative that designers and builders consider the issue of roof flashing as a key element of construction plan detailing, construction trade coordination, and field quality control. Oftentimes, inspectors discover flashing details incorrectly installed or even flashing that is missing. Manufacturers' recommendations and the industry's standards installation guidelines provide a valuable resource for inspectors to understand flashing details. All right, that was a good section. I think we are at 50 minutes, so we're going to take a 10-minute break. And while we take this 10-minute break, I'm going to review any questions you guys might have and see if we can answer them. So let me get to that section. All right.
Looks like we only have one question. Oh, there's two.
Web page on the storm stuff. So I will, Michael, I'll add the links that we went through here earlier. I will add them into the chat so you guys can see those. So thank you for that. And Mr. Burrows, how do the new smart vapor retarders fit in? So, well, let's go see here. Let me go see what you're talking about. this. No. Let's go open up. Let's see, what did you say? It was the smart. So let's see here. We're looking at like Weather Smart. So I'm gonna pull this. You guys should be able to see this screen. Weather Smarts is a weather-resistant barrier that balances water and air intrusion and permeability, featuring an advanced high-strength polymer technology. Its construction protects against the elements and provides tear resistance and UV stability. Weather Smart is suitable for any climate behind most exterior claddings and cooling fibers. Okay. Honestly, it looks like I don't know if this is the product that you were talking about, the smart vapor retarders. If this is what Brett Burrows, is this kind of what you're talking about, like the house wrap? Man, that's interesting. I don't know. Here, let's we're gonna go while we're in break, since we have no other questions. Installation instructions is what I'm looking for. Yeah. All right, so when humidity levels in the wall increase, membrane becomes porous to let excess moisture escape. Man, honestly, that we don't have any of that applied to any of the houses that I've inspected. So I haven't had a chance to dive into this. But it is very interesting. Honestly, the chemical technology, material technology is getting is getting so advanced and insane with the different types of modified plastics and that type of stuff. So uh, I'm sure because there is nothing in the code that talks about smart vapor retarders that it must be applied in the same fashion as standard vapor retarders. So um, while I'm not sure how they fit in currently, I'm sure that they still must be applied in the same fashion uh, as a standard vapor retarder. So now let me go. Somebody was asking about the links. I'm going to go back through here and see if I can find my links and share them in the chat. And we still got 6 minutes left of our break, so give me a second. So the figures that you can see on the screen provide models for correct flashing installation techniques for asphalt composition shingle roofing, which is the most common roofing material used in residential construction. For flashing details of other roof types, the inspector should refer to the manufacturer's literature and the industry guidelines. All right, so to avoid roof leaks, appropriate flashing details should be installed wherever possible. Roofing cement and caulk should not be solely relied upon for adequate sealing purposes. In addition, improper or missing kickout flashings, which may involve only a single roof flashing component, is associated with some of the more severe cases of localized moisture damage to walls. This flashing element is highlighted in Figure 7, which is on the left-hand side. It is commonly referred to as a kickout flashing or an end dam flashing or a diverter flashing. To ensure that ice dam flashing at the eaves, and then we're talking over here on the right-hand side. So to ensure that ice dam flashing at the eaves extends 24 inches horizontally beyond the exterior wall, the slope of the roof should be accounted for. Again, you're probably not going to be able to see this because ideally the shingles should all be tacked down and should not be able to be lifted up so that you can see that that it extends 24 inches horizontally. Again, so on the left-hand side, this diverter, kick-out flashing, or end dam is super important. And then if it's not, so for my inspection company, if it's not present, I do call it out as a monitor. So even if there is no evidence of damage or deterioration, or even if it was not required whenever the house was built, I still recommend that that it be upgraded or evaluated by a roofer and installed, because the amount of damage that it can cause with it missing is just it's so high. The cost of repair and fixing and building back after the damage is done is very important. Excuse me. Ugh. So let's see here. Uh, So now we have table 2, which is at the top here. It offers a nominal width requirements for the ice dam flashing at the eaves based on different roof slopes and the eaves overhangs. Note that for many scenarios, a single 36-inch roll of flashing may not be sufficient. Let's see. So again, you're probably not going to be able to see much of this besides maybe the apron flashing, remnants of the step flashing. If you're able to lift up the the shingle at the drip edge or along at the corner of the rake end, then you might be able to see the configuration of the underlayment. Other than that, most everything is going to be hidden away. But if you happen to if you happen to drive by and see the state of construction, if you know that you're going to be inspecting a house that is getting a new roof, you can definitely check for this other stuff. Let me see here. What else do we have? This is a diagram of the underlayment going over the drip edge flashing. And then on this diagram up here on the left, this shows you how the underlayment should go under the rake end. So under the rake end and over the drip edge. Roof ventilation and insulation. Roof system ventilation and insulation are important for a number of reasons: condensation control, temperature control, energy efficiency, and the prevention of chronic ice dam formation. Ventilation of attic areas is intended to prevent the accumulation of moisture vapor in the attic roof space and to dry low levels of condensation that may form on the underside of a roof deck. Ventilation is also intended to reduce the temperature of the roof deck during hot weather to improve shingle durability. Reducing the attic's temperature through ventilation and insulation also improves energy efficiency during hot periods. And in the case of ice dams, elevated attic and roof temperatures during winter can cause snow on the roof to melt. Insulation and roof ventilation help to keep roof's exterior surface cold and to help minimize the development of melted water and consequently ice dams. Ventilating roofs in extreme hot and humid conditions may add rather than remove moisture from attics and enclosed roof spaces. However, not ventilating roofs may void the asphalt composition roof manufacturer's warranty and slightly decrease the life expectancy of the roofing material due to increased temperature of the roof surface. Other tile, concrete, and metal roofing materials would not be similarly affected. Employing an unvented attic space may require designing the attic roof space as conditioned space, similar to that required when creating habitable space in the attic. There are several sources with more information on unvented attic designs. Traditional attic ventilation remains a cost-effective, though imperfect, solution for moisture control. In colder climates, roof ventilation serves to remove humidity and condensation from the roof attic space and helps to prevent the chronic formation of ice dams at the eaves. Before we get into ice dams, I have a great example of the lack of ventilation, what can happen with the lack of ventilation. So again, in my area, we are a hot, humid climate. And so because water vapor diffuses generally through our ceilings and then goes into the attic and then gets taken out of the roof by the airflow from the soffit vents up to the high roof ventilation. So that's our typical configuration here. So we got called out for an investigation inspection for a home that was recently remodeled. They got a new metal roof that was applied over shingle roof, and then there was some design features where framing was added for the roof to change what the profile of the roof looked like. And through that, the contractor was unfamiliar with building science and attic ventilation. And so because of that, they did not change because they added roof structure and then they put metal roof over the top of over the top of a previously shingled roof. And then they didn't change the airflow and the ventilation through the attic so that when the homeowner, and it was a vacation home, so they would come once a month and during the hot, humid months of the summer, they would come home and it looked like it had rained inside of their home and destroying electronics. Like all their electronics were ruined. They had moisture damage to a lot of their wood floors and so on. And so what ended up happening is that because they put the metal roof over the top of a shingle roof and they changed the structure, they did not change the ventilation. All that hot, humid air rose up to the ceiling, had nowhere to diffuse through, and so it condensed. It reached a dew point on the ceiling. It condensed, and it ended up raining inside of their home, causing thousands and thousands of dollars worth of damage. All right. So now to ice dams. What causes ice dams? An ice dam is caused by the warming of the attic space, obviously when there's snow or ice on the roof. And while the attic ventilation and the insulation contribute to prevention of ice dams by keeping attics cold, they can be overpowered by other attic warming effects, such as air leakage from the house into the attic through ceiling bypasses, chases, open gaps, uninsulated ducts placed in the attic. So if significant conditioned air escapes into the attic through bypasses, such as can lights are one of the worst locations, the attic ventilation will not be capable in preventing the warming of the roof decking and subsequent ice dams. Therefore, air sealing air leaks between the house and the vented attic is essential to making the attic ventilation work. Air leakage from the interior into the attic also introduces moisture. So if significant interior air leaks into the attic, attic ventilation may not be sufficient to prevent attic moisture and condensation problems. For enhanced protection against the formation of ice dams, Table 4 on the right-hand side provides recommended levels of insulation and vent area ratios as a function of venting layout. These recommendations should be found in areas with a ground snow load greater than 30 pounds per square foot and in other areas where ice dams are a concern. The recommendations for ventilation in Table 4 can additionally be used by contractors to create multiple lines of defense for flashing to prevent ice dam at the eaves. And also the arrangement of vent areas must balance high and low vent openings. So you want to make sure that you create that convection, that airflow that goes from the soffit out the roof. So if there's too much or too little, then you can run into problems. Roof overhangs and projections. So roof overhangs and projections, such as porch roofs and overhanging upper floors, provide a primary means to deflect rainwater away from building walls. Thus, the potential for water penetration through siding, windows, and doors is minimized. Because the protection of roof overhangs increases with increased overhang width, larger overhangs than those recommended in this section may be important in consideration of weather-resistant wall barrier design. Roof overhangs offer limited benefit during periods of severe wind-driven rain conditions, such as thunderstorm fronts and tropical storms, and in arid regions where rain is not a major concern. In severe wind-driven rain climates, a good performing weather-resistant barrier for walls is at least as important as providing roof overhangs. In high wind areas, overhangs add wind uplift load to the roof and may require stronger roof-to-wall connections. So I'm sure all of us have probably come across where you have an exterior door that has a larger sidewall going up above it. and no protective overhang or no roof line that covers it. And subsequently, when it rains, if the homeowner opens that door, if it happens to be an interior door, then they always get moisture intrusion coming in through the house. So again, another reason why overhangs and protecting your exterior penetrations is super important. So when you don't have those, I would pay special attention to the framing around the doors and the windows. Not so much windows because they should all be, they have the interior J channel and the flashing and all that kind of stuff. But in my area with my inspections, it's more often that we find damage around doors that do not have an overhang. So keep that in mind. Roof overhang should be based on climate. Recommended minimum widths for roof overhangs for 1- and 2-story wood frame buildings are shown in Table 5 and Figure 9. For taller structures, larger roof overhangs are desirable. Alternatively, porch roofs and upper floor overhangs can be used to protect lower story walls in accordance with Table 5. A decay hazard index map is provided in Figure 10 to assist in using Table 5. It should be noted that some U.S. building codes do not regulate minimum widths for roof overhangs. While roof overhangs and porch roofs protect building walls from impinging rain, gutters serve to protect building walls and foundations from roof water runoff. Roof gutters, downspouts, and leaders or diverters form the initial components of a drainage system for the building and site. A proper design of gutters and downspouts for water shedding, steep slope roofs should be looked for during an inspection. Common problems with guttering are associated with the installation and maintenance. Home inspectors can check if properly sized materials are being used, if guttering is appropriately sloped toward the adequately sized downspout, and if discharge is directed away from the building's foundation and perimeter. Discharging water at inside building corners should be avoided at all costs. Some local stormwater codes may require special infiltration or filtration treatments of roof runoff. So step 1 is design rainfall intensity. The rainfall intensity for roof drainage design is sometimes based on a 10-year return period and a 50-minute duration, seen in Figure 11. However, other design return periods and durations may be used effectively. Adjustment factors for other acceptable design conditions are given below, or you can see in the middle. A standard design criteria in the U.S. building codes does not exist, so practical experience and judgment are important. Then step 2, Step 2, roof drainage system spacing and layout. Based on a selected gutter size and type, as well as the design rainfall intensity from step 1, the maximum plan or the horizontal area of the roof that the gutter can adequately serve can be determined using Table 6, which is in the middle. Based on this area and the roof's geometry, spacing and locations of the downspouts can be determined as shown in the example. You can see down below. If using suggested sizes for downspouts, the gutter size will generally control the spacing of the downspouts. Downspouts with a dimension of less than 2 inches should be avoided. It is also generally recommended that downspouts should serve no more than 50 feet of gutter length. A commonly used gutter is the 5-inch K-style gutter with a 2 by 3-inch rectangular downspout. Roof rainwater collected in gutters and delivered to grade via downspouts must then be moved away from the foundation onto properly graded soil using leaders and diverters. This third component is just as important as the first two and should receive equal emphasis. Leaders should direct the downspout discharge a minimum of 2 feet away from the building perimeter, but is often referred to as 6 feet. So minimum of 2 feet, but ideally is 6 feet or more. This can be done using splash blocks or an underground drainage pipe, such as a corrugated polyethylene or smooth PVC piping, which discharges to a safe conveyance point. in particularly poor soil conditions such as expansive clays or collapsible soil, which has been severely weakened with increased moisture, the distance between the downspout discharge and the foundation should be increased. All right, so residential code 703 exterior covering. What is a weather-resistant exterior wall envelope, or a WRE? This section discusses what a home inspector should look for with weather-resistant wall envelopes, which can include siding, water barriers, etc. Current U.S. building codes don't distinguish between the inherent performance differences of the various weather-resistant envelope systems. In addition, selection of a siding system generally focuses on attributes such as appearance, cost, and durability. There are different types of cladding systems that protect a building from rainwater penetration and its accumulation in walls. This section is intended to show the home inspector the basic installations of the weather-resistant wall envelope as described in the 2006 IRC. IRC 703.1 says, exterior walls shall provide the building with a weather-resistant exterior wall envelope. The exterior wall envelope shall include flashing as described in section 703.8. The exterior wall envelope shall be designed and constructed in such a manner as to prevent the accumulation of water within the wall assembly by providing a water-resistant barrier behind the exterior veneer as required by section 703.2 and a means of draining water that enters the assembly to the exterior. Protection against condensation in the exterior wall assembly shall be provided. There are some exceptions. Due to the potential for water accumulation within the wall cavity, a water-resistant membrane must be installed behind any exterior siding and veneer. Under certain conditions, it is permissible to eliminate the membrane in detached accessory buildings or where the siding, finished materials, or the lath provides the needed protection. The following 2006 IRC language defines a water-resistant barrier. 703.2 water-resistant barrier is one layer of 15-pound asphalt, felt, or other approved water-resistant barriers shall be applied over the studs or sheathing of all exterior walls. Such felt or material shall be applied horizontally with the upper layer lapped over the lower layer not less than 2 inches. Where joints occur, the felt shall be lapped at least 6 inches. The installation of even the most weather-resistant wall envelope system on a house does not diminish the need for proper installation, particularly with regard to flashing details at penetrations. In addition, the use of roof overhangs provides performance benefits for all cladding systems by reducing the moisture load experienced over time and by allowing greater opportunities for the walls to dry in the event of a periodic wetting due to wind-driven rain. The life expectancy of various siding materials may vary widely, from 10 to as long as 100 years or more, depending on the type of material, climate exposure, maintenance, and other factors. Understanding a weather-resistant envelope system. You can see here, yeah, making that change allowed some wording to get mixed up here, so I apologize for that. But so you have face sealed, drained cavity, concealed barrier, and then there's another one here. Let's see, called the rain screen. Rain screen is not typical as a moisture resistant wall system, but we'll go over it here in a second. So face sealed. If a defect in the wall surface or joint detailing, such as caulk, exists or occurs over time, then water will penetrate and potentially accumulate in the wall, causing damage to any moisture-sensitive materials within the assembly. One example of this system is known as EIFS. However, building standards only allow the use of a new type of drainable EIFS, drained cavity on residential construction. Concealed barrier. This type of WRE relies on porous cladding material adhered to or placed directly on an internal concealed water barrier or drainage plane. A common example is conventional stucco. This WRE system also relies primarily on deflection of rainwater, much like the face seal system, but also has a limited capability to absorb moisture, to later dry and to drain moisture through weeps or the weep screed at the base of the wall. However, there is no open drainage pathway to allow water to freely drain from the concealed moisture barrier. And then drained cavity. There are many possible variations of this type of WRE. In general, a cavity exists to separate the cladding material from the surface of the moisture barrier placed on the structural wall behind the cladding. The depth of the cavity, however, may vary. For example, vinyl siding may be placed directly on the moisture barrier. For example, building wrap 15-pound tarred felt and still provide a cavity only restricted at points of contact, such as the nail flanges. A minimum cavity depth of 3/8 to ½ inch is sometimes recommended by use of vertical furring strips placed over the water barrier or the drainage plane. Furring and flashing details around windows and door openings must be carefully installed and carefully inspected subsequently. Drain cavities increase the life of exterior finishes on wood surfaces and promote drying of the wall assemblies after wetting episodes. For brick veneer, a larger 1-inch cavity depth is recommended to allow the space for the brick placement and the mortar excess. And then finally, you have the rain screen WRE. A rain screen can be considered an incremental improvement over the drained cavity approach. This type of WRE is uncommon in the US, but has been used to some extent in Canada to address severe climate conditions. By the addition of some details to help reduce air pressure differential across the cladding system during wind-driven rain events, water penetration into the drainage cavity is further limited. At a minimum, this approach involves the use of an air barrier behind the cladding to resist wind pressures. Thus, wind pressure across the siding, which is vented and not airtight, is reduced and is less likely to result in water being driven through the siding due to pressure differentials across the siding. Also, the cavity between the cladding and the water air barrier must be compartmentalized by use of airtight blocking or furring at corners of the building as a minimum practice. This feature prevents pressure differences on different surfaces of the building from communicating through a continuous cavity behind the cladding, which can cause unintended pressure differences across the cladding that drive rainwater through the cladding into the drainage cavity. Because many of the required components of a basic rain screen system are already present in a simple drained cavity wall system, drained cavity systems are generally considered a more practical alternative for typical applications. Site climate condition. So determining moisture resistant walls, climate conditions are categorized on the basis of for the potential of wetting of the walls, especially wetting from wind-driven rain. The exposure categories can be referred to as severe, moderate, or low. The above classifications are intentionally subjective as there are no clearly defined criteria in the US for assessing wind-driven rain and its effects on the building wall systems. However, wind-driven rain climate data, as well as other related climate indices, may help guide the classification of a local climate based on the categories. So again, we're all over the United States in this webinar. So, and again, this webinar or this class is available online, so you can go and review these diagrams for your area more closely. All right, step 2, assess the building exposure. The terrain surrounding a building impacts its exposure to wind-driven rain. The ratio of a roof overhang width to the height of the protected wall below also alters the exposure of a building to weather and wind-driven rain. Long roof overhangs relative to wall height effectively reduce the exposure. Similarly, increased shielding of the site against wind tends to reduce the effects of climate. Table 7 on the left-hand side may be used to determine a building's exposure level based on the climate condition determined in step 1 in the previous slide, the roof overhang ratio and the wind exposure. The exposure level then leads to a reasonable weather-resistant envelope approach in step 3. The exposure levels in table 7 can also be used on a smaller scale to get a sense of the exposure for a particular for particular faces of a building, or even for the specific envelope and elements, such as a window. Understanding the exposure in this manner can guide inspections of flashing details, the potential benefits of having greater overhangs, and so on. And then step 3, the weather resistant envelope. Based on the building exposure level determined in step 2, a WRE approach may be selected and installed based on expectations of relative performance. Alternatively, other factors may be reconsidered in the building and site design to improve protection from rain, such as the use of larger overhangs to protect walls. All right, so you can see the ratings used in table 8, which is above, is subject to adjustment by experience, but they range in good, fair, poor for the type of WRE system. And then you have the wind-driven exposure conditions in the table 7 on the left-hand side is defined as no shielding, partial shielding, or full shielding. Again, because we're all over the United States, everybody is going to be a little different. So I would highly recommend taking some time and going through the climate in your area, and use your own house as an example and figure out what your wind exposure is, what type of WRE would be the best in your area, and then that will give you an idea of what you should be seeing in your area. If an exterior water repellent coating to masonry is apparent, pay close attention to the face of the product to make sure that spalling is not occurring. Often the wrong product has been applied and is not permeable, causing water to be trapped inside, and the face of the masonry will spall due to capillary action, causing hydrostatic pressure, thermal expansion, and/or osmotic pressures. So these solid generally brick walls rely on deflection of rain as well as the ability to absorb moisture in sufficiently thick and durable wall system. However, even these mass walls can become overwhelmed with moisture intake during extreme wind-driven rain episodes, such as hurricanes and tropical storms. Water repellent surface treatments or coatings like latex paint may be applied to these walls to improve rain deflection and minimize absorption of water. However, such coatings should be semi-permeable to allow for draining towards the outside. Various water repellent treatments are available for concrete and masonry, but they vary in cost, performance, and effective service life. Limited research indicates that polysilicone, I don't know. I don't know how to pronounce that word. My apologies. Blended water repellents may provide the best water repellents and durability. Again, if you see a brick veneer that has a kind of like a sheen to it, that's applied over the brick and over the joints, and or if you see a paint, any type of color difference from that is different from the brick, pay close attention to the brick face. It should be obvious if it is not the correct application for that situation, in that if it's not permeable, you will often see the face of the brick spalling off the home. If it was newly applied, in my inspection reports, I would make a mention that some type of a masonry sealant was applied, especially if it's a different color. But and recommend long-term monitoring to determine whether or not it has a permeability to allow for moisture to dry to the exterior. You could also go a step further and ask, especially if it was recently applied, put something in the report stating, recommend asking the seller for the product that was applied, and then, your client or the buyer can use that information to figure out if it was the correct material or not. Let's see, we're halfway done. Okay, so checking windows and doors. So the three major window and door frame types used in conventional residential construction are wood, vinyl, and aluminum. Windows and doors can be key contributors to water penetration in walls from either flashing failures around these components or characteristics of the components themselves. This section discusses the features of window and door components that may reduce leakage and related moisture problems. Without careful installation of window and door components, it should be assumed that they will leak some amount of water into the wall cavity. Simply relying on window and door products that are labeled according to standard test methods does not necessarily guarantee that water leakage will not occur through frames into walls. Frames that rely on seals and sealants at internal and exposed joints will eventually leak water as these joints fail over time. The life expectancy of a window and door unit may vary widely from 10 to 50 years, depending on unit type and materials, exposure, maintenance, types of seals, sealants used at joints, and other factors. Frames that rely on welding of the joints rather than sealants will generally provide a longer moisture-resistant service life. Many units have weeps that allow water to discharge from the unit. These weeps should be free from construction debris and appropriately arranged relative to siding and flashing to drain water away from the wall. In the absence of relevant installation details for a specific application and combination of exterior envelope materials, the manufacturer should be consulted. In addition, industry standard installation guidelines may be consulted, such as ASTM E2112-01. Pay close attention to where the weep holes on the windows are. Sometimes you will have, especially when COVID hit and the backlog of windows was, 6, 8, 12 months. Some builders were taking vertical sash windows, and turning them on their side and making them horizontal windows, sliding windows. And so your weep holes were on the sides instead of on the bottom. While you don't see it very often anymore, on homes built during the COVID era, you might see those applications. High performance windows have a system for weeping intruded water that acts much like a rain screen wall system, as previously discussed. In severe wind-driven rain conditions and high exposure conditions, such high-performance window and door systems should be preferred for the same reasons that cavity and rain screen WRE systems are preferred. The recommendations above detailing, or to the bottom right, and door frames, the recommendations above detailing window and door frames can generally be checked by inspecting the manufacturer's technical specifications showing a cross-section of the unit, including dimensions, seals, thermal breaks, if included, and other factors that may create leakage paths, such as corner frame joints and mold joints in multiple window assembly. For my experience, when you have basically, you have two windows side by side, and you have that plastic mold joint that goes in the middle. That is, for whatever reason, is especially susceptible to moisture intrusion. So in and around those windows that have those mold joints, just pay special attention to your window seal, the wall below it, and if there's any moisture staining. Now, sometimes you're going to get condensation buildup, and that oftentimes happens on the edges of the windows. And so if you see moisture staining down there, that can be fairly common. But if you see moisture staining in the middle of a double window section that has that mold joint, then oftentimes that water is coming through that mold joint and coming into the home and is moisture intrusion. And again, so we are in my area. I think we're the climate map is well, I don't even know if it's been updated yet, but our wind-driven rain ratio for my area, while it used to be in Oklahoma, is slowly moving into my area in Northwest Arkansas. So we are having, we're getting more and more calls from clients asking, about moisture intrusion coming through windows, coming in through different penetrations, just due to the amount of wind pressure that is being exerted from the wind-driven rain during our high wind events here in my area. So let's see. There are marked differences in how window and door units manage water. Under wind-driven rain conditions, water will penetrate window frame crevices and seals between the sash and the frame. Under severe conditions, this water may even be forced through the window joints into the interior side of the window. Windows that perform best have adequate clearances between the sashes and the frame to allow water to freely drain rather than become trapped. A minimum gap of 1/4 inch is recommended to prevent capillary action from holding moisture in locations where it can be driven by wind pressure differentials past seals and through frame joints. Flashing of wall components. Water penetration and accumulation in walls are most commonly associated with flashing and detailing problems around windows, doors, and other penetrations through the weather-resistant wall envelope. In figure 17, you can see on the right-hand side of the screen, there are flashing details that are provided as general models for correct installation techniques. These are not presented as the only solutions to flashings because there are many, many other viable solutions, but as an example of a workable approach to protecting shell penetrations from water intrusion. So R703.8 says approved corrosive resistant flashing shall be provided in exterior wall envelope in such a manner as to prevent water entry into the wall cavity or penetration of water to the building structural framing components. The flashing shall extend to the surface of the exterior wall finish. Approved corrosion resistant flashing shall be installed at the following locations: exterior window and door openings, at the intersection of chimneys or other masonry construction, with projecting lips on both sides under and at the ends of masonry, wood or metal copings and sills, continuously above all projecting wood trim, where exterior, so continuous above all projecting wood trim. I got a really good picture of this at the end of the PowerPoint. That is still being done on new construction. So anyway, we'll get there. And then where exterior porches, decks, and stairs attach to a wall or floor assembly of the wood frame construction, at wall and roof intersections, and at built-in gutters. Flashing details for windows and deck ledgers are essential for preventing water damage to wall assemblies. The kick-out flashing detail is important to protect against water intrusion. A variety of manufactured window sill and door threshold flashing components, such as pre-molded pan flashings, are also available. These components are used to expel any water leakage at the base of windows and doors. Recommendations that address different building conditions can be found in the Energy and Environmental Building Association's Water Management Guide and various other industry resources. Here's a good example of flashings that you should see out in the field. This one on the left, this is your deck ledger flashing. I continually have to talk with builders about putting a deck ledger flashing on. It is shocking to me that I still have to do this, but their frame of mind, a lot of times, I almost always see it on a deck with no roof. But when you have a deck with a roof, they will use the roof as a means to not that where it says that it's not required. The deck ledger flashing is not required to be flashed because it's covered by a roof. And now, well, the middle part of the flashing is probably protected. The ends, which are the most susceptible to water intrusion, are not protected, especially when you have wind-driven rain events. So it's a battle, even in my area, on new construction, and it's even on million-dollar homes where I'm having to battle with contractors or builders. And they're stating that it's not required because the roof is cut or the deck is covered, and then they refuse to put it in. So oftentimes, because we are in a lot of people are moving to my area, and so builders are basically able to say whatever they want because homes are kind of in short demand, especially new construction. And so oftentimes when I call out the missing deck ledger flashing, the builder will refuse to do anything about it, and so the homeowner is on the lam for having to have that apply or have that reinstalled. So just stick to your guns, call it out, make sure that you're protecting your clients as best you can, and let them, handle it from there. You've done your job. In addition, so over here, the one thing that I wanted to point out is if you see here, this brick, how it's angled towards the outside, we get, again, because we have a huge influx of people coming in, we have a major shortage of qualified contractors. And so when it comes to masonry contractors, they're installing this brick flat. And so, and then just applying a lot of sealant to this penetration right here. So I call out flat brick windowsills and recommend them to be redone, and so that the brick is pitched towards the outside. Because a lot of times on new construction, the wood is not completely dried in. And so over the course of the first year of the home, the wood does completely dry in, and the wood, the wood framing of this wall will shrink just a little bit, and because the brick is attached to the structural sheathing, it pulls the brick down and subsequently will tilt the brick back to the inside. And so I carry around a little level with me. And if there is any question about if the brick is pitched towards the outside or towards the inside, we'll put the little level on there, make sure it is pitched out. And if it's not, we call it out and recommend the client. If it's new construction, we recommend the builder to address it. If it's existing construction, then it's up to the homeowner. If they want to negotiate that, obviously that's their prerogative. But they, in that aspect, if they're not willing to do anything, then I just recommend that they yearly go and check the sealant at all of those penetrations and continually maintain that sealant with that to ensure water intrusion does not get back behind them. And then the brick veneer flashing at the roof. A lot of times, and now this diagram is kind of grainy, what I want to point out here, but you have this counter flashing that goes over the top. A lot of times that counter flashing will be missing, and you'll just have the base flashing, and they just have a ton of caulk that is sealing that base flashing to the brick veneer. And so obviously we definitely call that out because the sealant that is at that intersection is the primary means to keep water away, from going in between the flashing and the brick. And caulking should never be the primary means of to deter water intrusion. So definitely we call that out. So keep an eye on those. And these three things that you see on this screen are seen on new construction, missing or incorrect all the time, not including on existing construction. Talking about caulks and sealants, man, it really did shorten my my words over here, so I apologize about that. So in the construction of a weather-resistant envelope, a WRE system, there will be joints and seams that require or at least benefit from the appropriate use and maintenance of caulks and sealants. In the absence of guidelines for specification and application of caulks and sealants in model building codes, this section provides valuable information for inspectors regarding their use. Where caulk is required by manufacturer's installation instructions, the specified caulk materials and methods should be followed carefully by the installer and then checked by the inspector. In general, caulks and sealants should not be relied on as the primary defense against water intrusion at joints in WRE systems. Flashing is preferred where feasible, even when caulk is additionally used. Standard quality caulk and application practices combined with shrinkage and swelling of the building's components usually result in the onset of gradual failure of watertight seal within a few years. Caulking can prevent water damage inside and outside of the home. When applied around faucets, ceiling fixtures, water pipes, drains, bathtubs, and other plumbing fixtures. Caulking can also be used to seal air leakage. Some general information regarding the types of caulks and sealants is provided in the table, including longevity, the best uses, and the appropriate types of joints for given sealants. With proper adherence to the manufacturer's installation instructions, particularly with respect to surface preparation, high-quality caulks and sealants can be made to endure for a reasonable length of time between maintenance and replacement, up to 5 years, or considerably longer when not severely exposed. Silicone rubber and urethane caulks generally give the best overall performance for applications to exterior building envelopes. For bath and shower applications, mildew-resistant silicone caulk is also available. A high-quality caulk installation requires appropriate ambient temperature, dry and clean surfaces, and an adequate joint gap to allow the caulk to act elastically without pulling loose from the two caulked parts. In addition, foam backer rod or bond breaker tape may be installed to create an appropriate caulk joint profile for adhesion and flexibility and durability. Inspection of caulking is strongly recommended. You can see here in the diagram that I think this is butylol rubber, latex, oil, and resin based. And I highlighted the shrinkage from 5 to 30%, 5 to 10%. So this is especially important in that, especially latex, latex is some of the cheapest caulk that you can get out there. And oftentimes contractors will use it for everything. And so when it's used, especially on the outside, and it shrinks 5 to 10%, then you're going to get your gaps, in and around your windows. So just pay special attention. If oftentimes you're not going to be able to tell exactly what type it is, but if there is any shrinkage, if it has any cracks, separation, any of that stuff, oftentimes it is not the correct. It is not the correct type. Let's see. All right, I think that's it there. All right, moisture resistant foundations. So many sites, when talking about building sites, many sites are considered normal and fall within standard conditions addressed in the residential building code. Oh, you know what? Actually, we are 50 minutes in. Let's take another 10-minute break. And if anybody has any questions, we can answer them. So we'll come back at, my time is 7 o'clock. I guess y'all's time is probably going to be 8 o'clock. All right, let's see here. All right, well, looks like maybe no questions, so appreciate that. Actually, let's see here. Just an FYI on window installations. Check the installation instructions, as many manufacturers use different ways they want the windows installed, i.e. Manderson and Marvin. Agreed. So Michael makes a good point. And that's why in the diagram, it states, used to, you would cut the WRE, which would be the house wrap, in an X fashion. You would wrap it on the top, wrap it on the sides, wrap it on the bottom. And while that is still recommended, that might not be required by the window manufacturer. So if you can find the model number of the window and there is any question about how it was installed or whether or not it should have a certain type of flashing or if it should have sealant applied around the exterior, definitely do your due diligence, do some research, and go and see if you can find out, how it should have been applied and whether or not it is missing something. So, moisture resistant foundations. Okay, so as I was saying, so many homes fall within the normal standard conditions in residential code. However, the use of marginal sites, which is becoming more and more common, without the proper site design, can result in costly mistakes such as foundation, structural, and moisture problems. Appropriate foundation elevations and drainage patterns for the site should be considered. Real quick before I get into this, here's a quick example, is that there was a subdivision site that was developed back in 2006, 2007, or 2006, I guess. And then when the housing bubble burst, the development went bankrupt. And so that the site development went 10 years probably without having anything built on it. And it was then bought up by a local developer. And then they started building homes on it again. Well, in that 10 years, site drainage and other construction had happened around this site. And so there's this bank of about 5 houses where after they built the homes, and there was definitely indicators of there being problems, but the builder went ahead anyway. So what would happen is that there was a pond that was in the field uphill quite a ways. I mean, it was probably 50, 60, well, it's probably further than that, it's probably 100 yards away. But because of all of the additional construction that was happening, more water was getting funneled into that pond. And the city, when the new developer bought it, they didn't make them redo the plans, the site map, and they didn't they didn't have a civil engineer come in. They didn't redo any of the drainage plans. But because all that other construction, that pond was taking more water, and every time it would rain, it actually overflowed. And when it overflowed, all of that water went in and around these 4 houses that were closest to it. We got called in to do an investigation, and we had to bring in all kinds of other civil engineers and other people to back up the claim for the homeowner that there was a problem that should have been addressed in construction. So just it goes to show you that even 10-year difference, the drainage plan can change. So just keep that in mind. If you're walking in a yard and it feels like you're walking on a waterbed, you know that there is definitely some water drainage issues there. So that being said, when the house is built, a site plan should be developed to do more than just locate the building and the utilities and demonstrate compliance with setbacks and other zoning requirements. The site plan should also account for a drainage plan that indicates the slope of the land, the drainage patterns that convey surface water from the building site. For sites that generally provide natural drainage away from building location, the main concern is establishing an appropriate foundation elevation to maintain drainage immediately adjacent to the foundation. So in that instance that I was discussing, one house only had water intrusion into the home. The water got high enough that it came into the home. All the other 3 or 4 houses, the yard was just affected. And then obviously over time, the foundation would be affected if they didn't do something about the drainage. Model building standards typically require a minimum of 6 inches of fall in ground level over a distance of 10 feet from the perimeter of the building. Providing for additional slope is a good method to offset future settlement of foundation backfill next to the building, unless the soil is moderately compacted or tampered during the backfill process. That is something that you're going to see oftentimes, is that, which I think there's probably a diagram here later. I know InterNACHI has a diagram of loose backfill applied to a foundation wall that does settle over time, and then eventually the water is not pitched, or the ground is not pitched away from the home. It actually is pitched towards the home, and then water will funnel towards the footer and the foundation. Poor site drainage of surface water is perhaps the most important contributor to foundation moisture problems. Wetness of the site, soil-bearing conditions, and slope of the site are key factors in making a decision on whether to build and how to build the house. When poor site conditions exist, they can often be overcome technically, provided there are no land use restrictions. However, the added cost of design and non-conventional foundation construction, such as elevated foundation and/or special drainage features, should be considered important aspects of the expense of building a house. It is usually very costly to correct. It is usually very costly to correct site drainage problems and foundation moisture issues after the fact. Therefore, the inspector must be very careful as to what recommendations he or she makes about a site with poor drainage. Moisture problems are often found in basement of a home or building. Even in dry site conditions, foundations are continually exposed to moisture vapor from the ground. When basements are used on sites with high groundwater or in areas with fluctuating ground moisture levels due to rainfall and water table changes, they are frequently exposed to bulk water. Therefore, foundations must address potential water leak through cracks and joints, capillary movement of water through foundation materials, vapor transmission of moisture through foundation materials, and condensation of moist air on cool foundation surfaces. The degree of protection required for any given site and selected foundation type is determined by the inspector to ensure it meets or exceeds minimum building code requirements. The building standards and recommendations in this section aim to teach enhanced moisture-resistant techniques. Foundations that create below-ground spaces on wet sites require special attention. During an inspection, attempts to remedy moisture problems through waterproofing may be observed, although such efforts could have a shorter lifespan than the building. Moisture protection of foundations by the owner or builder should err on the conservative side when there is reasonable doubt about the moisture conditions on site. The moisture-resistant practices presented in this course serve as a resource for inspectors and can be considered during the construction of a building. They are cost-effective compared to correcting moisture problems post-construction and reduce the risk of moisture issues in other parts of the building by protecting the foundation, which is a prominent point for moisture. This is particularly important if backfill practices are not reasonably controlled to prevent settlement. On flat sites, this may require mounding of the foundation pad and coordinating appropriate foundation elevations to promote drainage. On sloped sites, excavation and grading in the uphill direction must provide sufficient drainage away from the building perimeter and against the direction of natural water flow on the site. For steep slopes, a retaining wall at the toe of the slope may be necessary. Controlling grading and backfilling operations in typical residential construction is challenging. Common practice on many sites involves placing backfill with minimal effort to fill the hole. Proper backfill practices and grading will ensure that the foundation remains dry more effectively than other recommendations. Foundation drainage serves several functions, such as removing free water from the foundation perimeter, which reduces lateral load on the foundation wall. It also lowers the groundwater level around the building's footprint, especially during wet seasons. Basement should not be used where groundwater levels are near the basement floor level. Current model building codes require drains around all foundations enclosing habitable space, such as basements, unless soils are naturally well draining. A site-specific soil investigation or extensive local experience confirming consistently deep groundwater levels is needed before assuming soils are well draining. Where the foundation drainage system cannot be drained to daylight by gravity, a sump and pump must collect the water and discharge it to a suitable outfall, a safe distance from the building foundation. A drainage layer underneath the entire basement floor slab, coupled with weeps to a drainage system around the foundation perimeter, may be more effective in eradicating conditions where potential for high groundwater levels near the basement floor elevation exists. Experience has shown that diverting moisture with a drainage system before it enters the living space is more effective than trying to seal moisture out of the foundation. The terms waterproofing and damp proofing both relate to moisture protection, but are often misapplied or incorrectly used by inspectors. Damp proofing does not provide the same degree of moisture protection as waterproofing. Model building codes typically require damp proofing of foundation walls that retain earth and enclose interior spaces below grade. Damp proofing involves applying one or more coatings of impervious compounds to prevent water vapor passage through walls under slight pressure. Waterproofing measures are reserved for conditions with high water table or severe soil water conditions. Waterproofing involves applying a more impermeable membrane to the foundation wall and may include damp proofing plus a layer of 6 mil poly on the exterior below grade portions of the basement's foundation walls. Other single ply or built-up membranes may also be used. Waterproofing combines sealing materials and impervious coatings to prevent moisture passage in vapor or liquid form under significant hydrostatic pressure. Concrete and masonry construction will develop cracks due to shrinkage effects. These cracks widen over time, providing pathways for water intrusion. Controlling these cracks is important, even though cosmetic cracks often do not affect structural integrity. Horizontal reinforcement of the top and bottom of the foundation wall helps control cracking and prevent differential settlement. Epoxy sealant can be injected into cracks in masonry foundation walls to address potential moisture problems. Inspectors often find shrinkage cracks in poured concrete foundation walls, which may allow water penetration. Utility penetrations through foundation walls should be carefully sealed on the exterior face prior to waterproofing and backfilling. High-quality urethane caulks are most suitable for this application, and the wall construction should be inspected for penetrations due to voids or other problem areas and appropriately repaired and sealed. Due to inspectors working with both new and existing constructions, this discussion focuses on interior insulation systems for basements. Exterior insulation strategies, such as using foam insulation panels on the outside of the foundation wall, remain viable options for new construction. These panels provide a moisture-resistant insulation layer exterior to the wall, moderating the interior wall surface temperature and integrating with waterproofing or damp proofing. This requires shifting the house structure outward so that the sill plate protects the upper edge of the foundation insulation during and after construction, which you can see over here in this diagram. See the rigid insulation, and the sill plate is overhanging with so that it creates a continuous plane, and that the water and the wall cladding can correctly shed water away from the house. We find problems with this all the time in my area. A lot of times this is not pushed out, and so the siding terminates at the sill plate, and oftentimes you can see the gap between the sill plate and the exterior rigid insulation. Often, you might have to look up a little bit, but it's still visible, which it should not be. Basement wall finishes face unique moisture challenges. Approaches for insulating and finishing basement spaces vary depending on whether the construction is new or existing, and whether the basement is only being insulated but not finished. Existing basements have limited options for exterior foundation insulation. Interior insulation approaches using foam, which offer good moisture performance, require a fire-resistant covering such as wallboard, making them suitable for finished basements but ineffective for merely insulating unfinished areas. Experts in the industry have different strategies for basement finishing. A successful basement finish design must address exterior waterproofing, humidity control, and air sealing properly. The illustration shows a concrete foundation wall with exterior insulation using foam insulation panels on the outside for moisture resistance. The above grade wood frame wall, constructed of 2x6s, overhangs the foundation wall by up to 2 inches, allowing for additional rigid insulation over the entire wall assembly. This figure also depicts a sand layer beneath the floor slab. The interior insulation systems For interior insulation systems, the methods illustrated are becoming best practice in residential construction. This strategy is included here for those dealing with moisture problems under traditional practices. It is not meant to substitute for adequate waterproofing, drainage, humidity control, or air leakage control. Low permeability vapor retarders on the interior side of the basement finishes, like polyethylene sheeting and vinyl wallpaper, should be avoided as they trap moisture vapor moving through the foundation wall, hindering the drying process for new foundations. Unfaced fiberglass batt insulation and permeable paint finishes on gypsum wallboard are preferred for basement finish wall assemblies. Proprietary basement finish systems using rigid fiberglass insulating boards have performed well. However, certified installers may be required by manufacturers. Rigid foam creates a moisture-resistant material buffer between finish wall materials and the basement foundation wall. Semi-permeable rigid foam insulating sheathing products like EPS or XPS should be used, since below-grade portions of the foundation wall must dry towards the interior. Product specifications should indicate a perm rating greater than 1 perm. Joints in the foam sheathing must be taped and sealed. If additional insulation is desired, a frame wall can be built and cavity insulation installed as shown in Figure 25, which is this right side here. To prevent humid basement air from leaking into the finished wall assembly and condensing, the interior side should be sealed against air leakage. The ideal approach uses gypsum wallboard as an air barrier, requiring sealing any panel penetrations or leaks. Air sealing basement ceiling penetration should also be addressed. Additionally, joints in the foam insulation should be taped and sealed. Gypsum wallboard, wood trim, and wood framing wick moisture from the slab, cooling materials in contact and creating higher surface humidity levels, potentially supporting mold growth. Finishes and baseboard trim should be held a ½ inch above the slab surface, sealing gaps with caulk or sealant to prevent indoor air leakage into the wall assembly. A thin foam plastic sill sealer may be used underneath the finished wall's bottom plate for added moisture protection. During basement inspections, check the bottom of the finished wall for moisture. Slab on grade. Construction includes thickened edge or monolithic slab foundation construction. Given their similarity, concrete or masonry stem wall foundations with an independent above grade slab floor will be discussed. Moisture resistant installations are summarized in the diagram. They are relatively simple in comparison to the requirements for basement construction. However, many of the same principles apply. Slabs below the outside ground level, as with partial or full basement construction, should be built in accordance with the basement foundation recommendations. A good understanding of the best practices for moisture-resistant construction will greatly improve the inspector's ability to search for and diagnose moisture problems. A vapor barrier of 6 mil poly or equal or approved vapor retarder is generally required below any slab intended as a floor for habitable space. The joints should be lapped not less than 6 inches. It should be placed in direct contact with the underside of the concrete slab. The vapor barrier will prevent moisture vapor from adding to the building's interior moisture load and also serves as a brake to the capillary movement of moisture. A vapor barrier is a vapor retarder of a certain class 1 vapor retarder. A capillary brake layer, generally 4 inches of clean graded sand, gravel, crushed stone, or crushed blast furnace slag, further prevents bulk soil moisture from wicking up to the bottom of the slab. Building codes typically require a capillary layer below the slab, and this should be provided under the vapor barrier so that water cannot be trapped in the gravel layer between the vapor barrier and the slab. The vapor barrier will help to cure the concrete properly if it is properly damp cured on the top surface by preventing exposure to excessive drying conditions and if the excessive water in the concrete mix is avoided. Something to keep an eye out for is that if you go into a home and the perimeter of the house, now it could be the entire perimeter, it could be a section of the perimeter, and especially on wood flooring, if you happen to have wood flooring on a concrete slab, pay attention to the perimeter, the outside area of the slab, and if the wood flooring is of a darker color against the perimeter of or against the interior perimeter than it is on the middle perimeter, oftentimes the vapor barrier or the vapor retarder was cut too short and is out here, and so moisture is still flowing upwards, and it's getting into the slab and then going through the slab and coming into contact with the wood flooring. So just keep an eye out that when you're doing your inspection, if you see where the wood is darker, and especially if there's not a window up above it or a door near it, and the wood flooring is darker on the perimeter, oftentimes I would use my moisture meter and check that area. And if you get elevated moisture levels, I would call that out to the client and recommend them to, if it's rotted, it's a problem. There's going to be a great picture of this at the end of the presentation that will explain this a lot clearer. But definitely call that out in your report if you see that and recommend it for monitor or further investigation. All right. Slab on grade construction, concrete will crack as a normal outcome of the curing process. Cracking can be worsened if uneven bearing conditions, such as uncompacted fill areas, exist under the slab. The use of welded wire fabric reinforcement provides a means of controlling the severity of the cracking. And while fiber reinforced concrete may also provide adequate crack control, the introduction of fibers may tend to decrease the workability of wet concrete. Excessive use of water for workability will tend to allow moisture to more readily penetrate the concrete slab, weaken the concrete, and lead to differential drying issues and cracking. Excessive cracking can allow additional moisture as well as radon gas to penetrate more easily through the slab. Concrete control joints may also be used to control random cracking by creating planned lines of weakness in the slab. Shrinkage and curing cracks generally occur in any continuous length of concrete greater than about 12 feet. As with basement foundations and footings, the local building code may not require horizontal reinforcement of the thickened edge footing of a monolithic slab on grade. The same applies to stem wall and independent slab construction. However, the information in this course describes a minimum of a continuous number 5 rebar located horizontally at the top and the bottom of the thickened edge of a monolithic slab or stem wall. This allows the thickened slab edge, the footing, to act as a moderately reinforced grade beam to reduce cracking from differential settlement. Concrete and masonry stem walls may be reinforced with horizontal reinforcement bars in a manner similar to that recommended for basement walls. For difficult site soil conditions, such as expansive or weak soils, other types of concrete slab foundations may be required or advisable, such as mat foundations or post-tension slabs. Building codes allow foundation insulation to be placed in various locations at the perimeter of a slab on grade foundation. Ideally, the best location for insulation in the slab on grade foundation is on the vertical outside face of the foundation. In this location, thermal bridges are minimized, energy efficiency is maximized, and the slab surface temperature is moderated to prevent the risk of condensation during cold weather. If slab on grade insulation is placed in a different location, such as on the inside face of the perimeter foundation wall, then care should be taken to create a continuous thermal break between the indoor portions of the slab and the exterior. Like basement wall finishes, finishes on concrete floor slabs on grade are exposed to a unique environment due to direct ground contact. From a moisture perspective, tile, terrazzo, stained decorative concrete, and other moisture-resistant finishes are ideal for slab on grade construction. These materials are resistant to flooding and other sources of moisture damage and are typical in southern and hot, humid climates. If a slab shows signs of pre-existing moisture problems such as dampness or condensation, salt deposits, standing water, then the issue should be addressed before moving ahead with finished flooring. Once any pre-existing moisture issues with the slab are addressed, a floor finish assembly that can accommodate a small amount of upward moisture flow can be installed. One viable approach involves the use of rigid, semi-permeable insulated sheathing greater than 1 perm, such as extruded polystyrene on top of the slab, with 12 to 16 inch on center furring above the foam, followed by a layer of tongue and groove plywood for the subfloor. The finished flooring above the plywood should be a breathable finish, so impermeable materials such as vinyl flooring should be avoided. With this type of assembly installed, a relatively dry slab with a sub-slab layer of poly can be finished and designed to accommodate a limited amount of moisture that dries upwards. The primary cause of moisture problems in crawl spaces are poor site drainage, lack of a ground vapor barrier, and ventilation during humid summer conditions. Crawl space moisture damage and mold formation can be caused by these issues and must be addressed for moisture-resistant crawl space foundations. Ideally, crawl space construction should result in an interior ground surface at or above the exterior finished grade. Extra attention is needed for foundation drainage with crawl spaces below the exterior grade. Venting crawl spaces in humid conditions can cause condensation on cool surfaces, including ductwork, floor framing, and potentially leading to water accumulation, wet insulation, material degradation, and mold. Ground cover laid on a crawl space floor can become damaged over time, reducing its effectiveness and making drainage difficult if wetted from plumbing leaks. As an enhancement, a mud slab, which is a 2-inch thick concrete slab, may be placed on the ground cover and sloped to drain to a sump pit for wet sites. If the crawl space elevation is below the exterior finish grade, foundation drainage and damp proofing, such as a bituminous coating, should be provided as required for basements. Crawl spaces should use these measures along with exterior drainage systems. There are 2 choices for crawl space ventilation: Conventional practices, which require minimum net area openings based on the underfloor space area, or non-vented design strategies. Traditional ventilation calls for a minimum net area of at least 1 square foot for 150 square feet, or reduced to 1 square foot to 1,500 square feet when using a Class 1 vapor retarder. Vents should be on at least 2 opposing sides of the foundation, near corners, and high on the foundation walls. Inspectors should refer to applicable building codes before recording evaluations. Non-vented crawl spaces are also recognized as suitable, especially in hot, humid climates where outdoor air adds moisture. This method involves several factors: functional exterior grading and site drainage, minimizing air leakage between outdoors and crawl space, insulation on the perimeter walls, such as rigid foam, and the use of 6 mil polyethylene ground cover, damp proofing of the foundation walls, and some ventilation with conditioned air. Recent model building codes require a non-vented crawl space to be supplied with conditioned air and a return air transfer grill or mechanically ventilated. Inspectors should check local codes when inspecting these crawl spaces. Understanding vented versus unvented crawl spaces. Vented crawl spaces can minimize radon and moisture-related decay hazards by diluting crawl space air, but do not necessarily solve serious problems. Disadvantages include insulation needs against heat loss freezing, increased insulation area and costs, and potential moisture issues in wood. Operable vents can reduce winter heat losses and keep out moist air in the summer. Venting is unnecessary for moisture control if open to an adjacent basement and incompatible with crawl spaces used as heat distribution plenums. Unvented crawl spaces may reduce insulation needs and simplify installations, minimizing condensation hazards. Many agencies are unwilling to endorse closing vents year-round due to common moisture problems. Soil type and groundwater level influence moisture conditions, and crawl space can be designed as a short basement with slurry slab floors, generally less susceptible to moisture. The main distinction between unvented crawl spaces and basements is accessibility and likelihood of noticing moisture problems. Decay of common wood framing materials can begin when moisture content of untreated wood exceeds 20%. In foundation and building applications, these conditions should be avoided by adherence to minimum ground clearances and detailing requirements. The ground clearances outlined in this section are considered minimums that have worked reasonably well in typical climates. In climates with frequent rainfall or sites with continuously moist ground conditions, greater clearances are recommended. In addition, capillary breaks are important, particularly when clearances are at minimums. Capillary breaks help protect wood from wicking up moisture from the foundation, around the foundation from the ground. Capillary breaks may be in the form of materials such as metal flashing, tarred felt paper, sill sealer foam stripping, and polyethylene. When wood has direct ground contact, or if clearances are less than those required, then preservative treated wood or other moisture resistant materials should be used. Most building codes require a 6-inch minimum clearance between untreated wood and the exterior grade, and some codes allow a 2-inch reduction in this clearance if brick veneer separates the internal wood materials from the exterior grade. A minimum of 8 inches of clearance between untreated wood and the exterior ground level is recommended by many experienced building inspectors. In other conditions, ground clearance recommendations vary. For example, floor beams and crawl spaces are required to have a 12-inch minimum clearance to the interior grade, as much for reasons of access as for moisture protection. Often there are situations where wood cannot be adequately separated from ground moisture or protected from exterior moisture sources. In these situations, either naturally decay-resistant wood or preservative-treated wood must be used. In some cases, wood alternatives can be used, such as plastic porch posts with metal pipe inserts, plastic decking, concrete posts or piers, or plastic lumber composites. The focus of this section is on identifying proper specifications and use of preservative-treated wood to ensure moisture decay resistance and durable performance. The recommendations in this section are based on the standards and recommendations of the Southern Pine Council and the American Wood Preservers Association. In recent years, changes have occurred in the availability of certain wood preservative treatment chemicals for the use in residential projects. Therefore, it is important to understand how these changes affect treatment requirements for various types of wood and applications. In particular, the use of CCA, chromiated copper arsenate, has been discontinued as a wood treatment except in certain commercial and agricultural applications. However, there are exceptions. For example, CCA treated lumber and plywood are still available for use in permanent wood foundations in residential as well as commercial and agricultural applications. For most residential applications, however, newer forms of treatment are the only choice. It is important to realize that many of the newer lumber preservative treatments may increase the corrosion rate of galvanized fasteners by a factor of 2 or 3 under standardized test conditions. Therefore, in cases of exposure to moisture at decks, porches, and balconies, it is recommended that stainless steel fasteners and connector materials be considered. At a minimum, hot dipped galvanization or G120 galvanic coating should be specified for steel fasteners and cold form steel connectors. A G120 coating provides at least twice the galvanic coating commonly used for framing connectors in residential construction. Connectors within the building envelope that are in contact with newer lumber preservative treatments are generally exempted, such as half-inch diameter sill anchor bolts. Other types of foundation wall construction methods and materials are less frequently used in the United States, including permanent wood foundations, insulated concrete forms, although it's becoming more and more common, precast concrete foundations, which is kind of common in my area, and elevated foundations in flood-prone areas, which is also common in my area. These systems are not specifically addressed in this course, except to mention that there are important foundation moisture management practices that may be required. The inspector should carefully consider manufacturer and industry recommended practices in addition to any minimum building code requirements when inspecting these types. Other proper consideration and installation, these systems provided dry, serviceable foundation systems. In the northern US, moisture vapor problems are driven primarily by indoor relative humidity combined with low outdoor temperatures during the winter. In southern US, especially in the southeast, the problem is largely driven by high outdoor humidity and low indoor temperatures during summer months. Mixed climates are exposed to both conditions and can experience both types of problems. Therefore, many of the best practice recommendations in this section vary according to climate. The same is true of the underlying building code requirements. Unfortunately, there is no definitive and widely accepted climate map that addresses all climate factors that contribute to moisture vapor problems. There are perhaps too many variables in climate and construction practices to treat the issue without significant use of experience and judgment. Various climate maps and criteria have been applied in building codes in the past, and more recent building code changes continue to demonstrate a lack of overall agreement among experts. It is for these reasons that acceptable practices for moisture vapor control often vary based on local experience and difference of opinion. Moisture problems related to water vapor can be confusing because they're caused by several types of moisture sources and can result from different types of dynamics in a house. Also, seemingly unrelated decisions that are made for one building system, such as how to lay out the HVAC system, are not at all independent and will affect the migration of water vapor in a house. High indoor humidity, greater than 40% in the winter and greater than 60% in the summer as a general range, is a primary cause of many vapor-related moisture problems in homes. From a moisture perspective, very low indoor relative humidity levels are helpful to control condensation and related problems. But other important factors that actually require some minimum level of indoor relative humidity to be maintained must also be considered. These include a minimum humidity level to keep occupants comfortable, which is approximately 25%, minimum humidity to keep wood finishes and furniture from drying out, and for homeowners with special needs for higher indoor humidity. When interior relative humidity levels are a concern, whole house and spot ventilation to the dry outdoor air can be installed, and ventilation controls that automate spot exhaust could be added. High relative humidity levels might be a concern based on local experience and climate, high expected occupancy loads, unusual occupant habits, or especially tight construction. Providing for increased ventilation means selecting higher capacity fans for whole house or local ventilation devices. One option is the continuous fan operation at a low level with local switches that can boost the fan speed temporarily. In humid regions, the addition of a damp outdoor air without any treatment of this new moisture load will actually add moisture to the house instead of helping to control indoor relative humidity. Heating, cooling, and ventilation systems in such climates should be operated to accommodate additional moisture loads resulting from ventilation. Inspectors should consider documenting the existence of any supplemental dehumidification that is observed during an inspection. The presence of a dehumidifier the presence of dehumidifier units may indicate the homeowner's concern about humidity or moisture. Supplemental dehumidification systems address indoor relative humidity by managing both built-in moisture in new houses, like water that dissipates from new concrete basements, and ongoing moisture loads in existing homes. Controlling ongoing moisture loads is especially important in areas with humid shoulder seasons, when the AC system will not operate for cooling, but indoor humidity must still be removed. Air leakage. Let's see where we at. Air leakage can transport significant water vapor, impacting moisture issues in buildings. To minimize air leakage, building envelopes should be sealed with an appropriate air barrier system considering climate conditions. Home inspectors must understand air leakage dynamics. Factors driving air leakage include wind, stack effect, and forced air HVAC systems. Air barriers help mitigate these issues. However, sealing practices might reduce combustion air supply for fossil fuel equipment, causing backdrafting of combustion products. Sealed combustion equipment and mechanical ventilation are recommended to address safety concerns and indoor air quality. Air barrier materials must manage vapor movement and water shedding based on their location within the wall. Building codes mandate air sealing around framing joints, utility penetrations, drop ceilings, and other areas to prevent air leakage. Suitable sealing materials include air barrier materials, caulks, sealants, tapes, and gaskets. Inspectors should prioritize major air leakage points such as mechanical chases, attic access hatches, plumbing stack penetrations, and exposed wall cavities. Cathedral roofs require careful sealing to prevent condensation and moisture problems from humid indoor air entering cold roof cavities. Reducing air leakage is essential, and air barrier systems aim to block leaks while addressing rainwater protection and vapor retarders. Effective air barrier materials include gypsum wallboard, spray polyurethane foams, wood structural panels, foam boards, and building wraps. Seams in these materials must be sealed to ensure low air permeability. In cold and very cold climates, the primary concern is preventing interior warm and humid air from flowing outward into the building's exterior envelope assemblies during winter months. This airflow can carry a large amount of moisture and cause condensation in the wall. Therefore, the use of an interior air barrier system in cold and very cold climates is preferred and may be combined with a warm and winter vapor retarder. A viable approach in such regions is the ADA method, used in conjunction with an interior vapor retarder layer, such as craft-faced bats or vapor barrier paint on drywall. Use of an APA method should be applied more cautiously, as some localities and building scientists are concerned that the poly layer is almost too airtight and vapor impermeable, and so will not allow drying to the interior of the building at any time of year. Okay. The APA method. So the airtight polyethylene approach is what we're talking about here, and the airtight drywall approach is what we're talking about there. So ADA method, APA method. In damp and humid climates, the primary concern is preventing exterior warm and humid air from leaking inward through exterior surfaces into building envelope assemblies that will be cool from the air conditioning. In damp and humid climates, an air barrier system is preferred on the outside of the wall. Many exterior sheathing products and wraps can provide this function and can also serve the water barrier function underneath siding materials, which is the ASA and the AWA method. In climates with mixed conditions, the most suitable air barrier system can be selected based on other construction characteristics and then combined with these systems. For example, if building wrap is used as part of a drained cavity weather-resistant envelope, then the airtight wrap approach, the AWA, which is this guy here, can be used with a little extra detailing of the building wrap, such as taping the overlapped seams. Similarly, extra attention to sealing interior drywall joints and penetrations can make the airtight drywall approach, the ADA, a reasonable strategy. In hot, humid regions, walls must dry towards the interior. Homeowners should avoid non-breathable finishes like vinyl wallpaper or vapor barrier paint. Vapor retarding materials on the inside can cause condensation issues. Use semi-permeable materials such as unfaced fiberglass bats with permeable interior paint. Incorrect installation of vapor retarders often cause moisture problems. Vapor diffusion, high indoor humidity, and air leakage contribute significantly to these issues. Properly installed vapor retarders prevent humidity within the building assemblies. In hot, humid climates, exterior wall systems should dry inward by placing vapor retarders outside and keeping interior materials vapor permeable. In cold climates, walls should dry outward by using vapor retarders inside and ensuring exterior materials are vapor permeable. Common sheathing materials with low perm ratings may impede drying, which is under investigation by building scientists. This section describes moisture control and moisture-related problems concerning the design, installation, operation of mechanical systems, such as heating and cooling, equipment, ductwork, and ventilation. Common moisture issues that can arise from residential mechanical systems are covered. Commonplace rule of thumb sizing methods, such as 1 ton of cooling per 400 to 800 square feet of conditioned floor area, should not be used in place of a building-specific load calculation method, meaning the manual J. Although still potentially a problem, oversizing of AC systems from using the rule of thumb methods causes increased short cycling of the cooling equipment. Short cycling reduces energy efficiency and can decrease moisture vapor, latent heat removal capability of conventional AC equipment by as much as 1/2 of the rated latent heat removal capacity. This has two negative effects. First, indoor relative humidity levels are increased as the AC system reduces the air temperature but removes moisture to a much lesser extent. Second, due to increased indoor humidity and discomfort, occupants may lower the thermostat set point temperature to compensate. As a result of cooler indoor temperatures, approximately less than 75 degrees, and higher indoor relative humidity levels, condensation is more likely to occur on windows and doors and on the inside of wall cavities on concrete floor surfaces and on floor sheathing and joists above crawl spaces. For these reasons, this guide emphasizes the importance of using the ACCA Manual J, or other similar cooling load calculation procedures to size HVAC equipment. Even with proper sizing of heat pumps for heating and cooling loads, there are significant times of the season where the system will operate under part load conditions rather than the design load conditions. Thus, accurate sizing of equipment only lessens the short cycling problem. To provide improved moisture removal and energy efficiency, 2-speed compressor heat pumps with variable speed blowers should be considered. These systems operate on the lower capacity much of the time, providing enhanced moisture removal and more efficient operation. Such systems offer the greatest benefits in areas with long cooling seasons and are also a good match for 2-zone systems because they can effectively handle single or dual zone operation. Supplemental dehumidification controlling indoor humidity and damp humid regions or enhanced moisture removal from HVAC equipment is recommended in damp humid regions as a means to control indoor moisture levels. In other areas with less prolonged periods of high humidity, these systems should still be considered based on their benefits, such as better control of indoor moisture, enhanced comfort, and integration with fresh air ventilation. For new basement foundations, supplemental dehumidification will also help remove moisture from the foundation as it dries, which can help prevent moisture problems in finished basements. Supplemental means some type of dehumidification equipment besides the house AC system. These systems range in cost, quality, and function. A few dehumidification systems options are as discussed. Portable dehumidifiers, stationary dehumidifiers, and dehumidifier ventilators. Sealed combustion chambers should not create moisture problems. The use of sealed combustion HVAC equipment is ideal because it helps to alleviate potential backdrafting, and it also helps to control pressure differences across the building envelope. Controlling air pressure differences across the building envelope helps to minimize air leakage and migration of moisture into building assemblies. Sealed combustion equipment, such as sealed combustion natural gas furnace, draws all air for combustion directly from the outdoors via a dedicated duct and combusts the air and fuel in a sealed combustion chamber. Building codes require that, sealed ducts reduce air leakage and moisture. Building codes require that joints and duct systems may be made substantially airtight by means of tapes, mastics, gaskets, and other approved methods. This guide recommends sealing duct systems such that air leakage to the outside of the building envelope is less than or equal to 5 cubic feet per minute, or 25 by 100 feet squared of floor area. I see. Served by the system. The measurement CFM25 denotes the air leakage from the duct system measured at the duct pressure of 25 pascals. Actual testing of the duct system with a duct blaster test can be conducted by home energy raters or utilities. Suitable sealing materials include UL 181 rated foil tape and mastic. Sealing air leakage from ducts has two important advantages. First, it improves HVAC system energy efficiency, and second, it reduces pressure imbalances that can cause air leakage through the building envelope. We have more content to get through. I'll answer your question when we get to the end here. This air leakage can transfer a large amount of moisture into building assemblies and can cause condensation and related problems. For example, a house with leaky supply ducts in the attic can become depressurized, resulting in warm, damp outdoor air being drawn into the building envelope during the cooling season, a particularly troublesome problem in hot, humid climates. Airflow can transfer moisture vapor through and into building assemblies in amounts of 10 to 100 times more than that which would typically occur by vapor diffusion. Conversely, building pressurization from leaky return ducts can cause humid indoor air to exfiltrate into the thermal envelope, where it may condensate on cold surfaces during winter conditions. Inadequate air returns cause moisture problems. Most central return systems do not provide adequate pathways when interior doors are closed because door undercuts do not provide enough flow area for the return air. As a result, some interior spaces become pressurized and others become depressurized. Both of these conditions can drive air leakage and moisture transfer. An ideal return air system provides unrestricted pathways for return air to travel to return grills. To achieve this type of return system, the inspectors should see multiple returns with the ducts formed from actual duct materials and not building cavities, or jumper ducts that transfer grills to provide return air passageways from rooms that can be isolated when interior doors are closed, which is moderately effective and moderately expensive, but may carry privacy objections. So what's that dark stain on the carpeting's perimeter? In addition to alleviating pressure imbalances and limiting air leakage through the building envelope, these practices can also improve comfort and eliminating soil problems that leave darkened stains on the perimeter of carpets. Whole house mechanical ventilation is good, and whole house mechanical ventilation systems are recommended to provide fresh air and help control a range of indoor air contaminants. Systems should be designed based on the ASHRAE standard 62.2, ventilation and acceptable indoor air quality in low-rise residential buildings. The benefits of having a whole house ventilation fan installed can be conveyed to the homeowner client. Tell you what, we're gonna skip down to this section. It is not uncommon for a home inspector to find clothes dryers vented to an indoor or enclosed building space, such as crawl spaces. It is also common to find bathroom exhaust fans vented to the attic space or merely directed toward an attic vent. These practices are prone to create moisture vapor problems and should be avoided. Home inspectors should recommend that all exhaust vents be directly vented to the outside by attachment of the exhaust vent ducting to appropriate through wall or through roof ventilation fixtures or grills. Exhaust ventilation ducts should also be attached and supported like any other ductwork. Finally, exhaust fans are rated like 50 CFM based on the limited amount of back pressure due to the type and length of the ductwork and bends in the ductwork. Therefore, duct lengths longer than 25 feet, less 5 feet for each 90-degree bend, should be avoided unless appropriately designed. If long duct runs are unavoidable, larger capacity fan units should be used. Holy moly. We've got only a few more minutes here. I'm trying to get through. So efflorescence is the white chalky powder that you might find on the surface of a concrete or brick wall. It can be a cosmetic issue, or it can be an indication of moisture intrusion that could lead to major structural and indoor air quality issues. A home inspector should understand what efflorescence is in order to recognize potential moisture problems. Efflorescence is the dissolved salts deposited on the surface of a material such as concrete or brick that are visible after the evaporation of the water in which it was transported. The moisture that creates efflorescence often comes from groundwater, but rainwater can also be a source. Efflorescence alone does not pose a major problem, but it can be an indication of moisture intrusion. Let's see. Porous building materials are capable of wicking water for larger distances due to capillary action with a theoretical limit of capillary rise of about 6 miles. That's 6 miles directly up. Think of a tree and how a tree can transport water from its roots to its leaves. That is capillary action, and it's very powerful. When you add salt to the capillary action, it becomes destructive. Here's a great video. Hopefully you guys can see this of how a brick soaks up water. If it'll play. So bricks are like sponges. And so if you have a house with no gutters and you have a brick siding or brick cladding, negative grading, all that water is falling back next to the foundation and is soaking back up the exterior brick cladding. Water in all its forms is an ever-present fact of life, especially for homeowners. Households commonly use and dispose of hundreds of gallons of tap water on a daily basis. Torrents of rainwater must be successfully shed by the roof and the walls during thunderstorms. Groundwater travels through the soil beneath the foundation. We control indoor humidity levels for maximum comfort, and the house itself absorbs and releases moisture in the forms of condensation and water vapor. All right, so here are a few factors that contribute to indoor humidity. Cooking, when you heat food up, it is pulling the moisture out of whatever you're cooking, so that can attribute. Dishwashers attribute, and obviously leaks under sinks can attribute. Bathrooms, obviously hot, humid showers, leaks under the sinks. Just normal use of a bathroom can affect indoor quality. And so this is what I wanted to get to because we are about out of time. So this is a diagram that I wrote up. This is what I was talking about, how now this client on the left-hand side, the issue was not the 6 mil poly underneath underneath the poured foundation. The issue was how they applied the brick veneer and the wheat poles, and then the builder promoted the fact that they used 6 mil poly to attach to the exterior wall sheathing and then embedded it in the grout in the mortar joint. And then they had backfill that backfilled up against the brick. And so moisture was traveling through the brick, going up the air gap. And because they used the 6 mil poly, they actually left the sill plate exposed. And so the moisture traveled through the sill plate, through and into the wood flooring. And so the entire perimeter of this house had they had like a blonde type wood flooring. And around the entire perimeter it became became a lot darker brown instead of blonde. And so they kept calling the builder. The builder had no idea what was going on. I was called out to investigate, and we were able to take out a row of brick next to a weep hole. And then this is what we found. We found the 6 mil poly. The painter actually painted in the weep holes, so there wasn't even airflow going through the weep holes anyway. And then the brick masons, so much mortar fell down the backside into the air gap that it actually created a brick cap or a mortar cap on top. So the only airspace that the weep holes, if they weren't painted, the only one that they were transferring air from is in this small section here. So the fix was well, the only fix that the builder was willing to do was come down below the 6 mil poly and apply a new and install new weep holes to allow for air transfer. And then they're just going to wait a year and see if the moisture content of the wood flooring goes down. Again, here is a good example of why kickout flashings are so important. So here's a missing kickout flashing on a chimney chase, and then here is the damage associated from the missing kickout flashing. And then lastly, so these are pictures that I took. So this is the crawl space. There was not enough crawl space ventilation. So the moisture, the cold duct was creating condensation because of the lack of airflow in here, and it was soaking into the I joist and into the subfloor. And this was a $1 million home, and this was happening at nearly every floor register. I think we were at like 3,500, 4,000 square feet. So we had, probably 20 floor registers that this was occurring at. This guy here in the middle, this is very common to see in my area. You have the metal veneered garage door trim. This you can always tell when a builder buys plans off of the internet and doesn't have an architect design. So this house was originally designed for brick veneer. They modified the cladding and added cement fiber, board and batten. And when they did that, they did not adjust the honestly, if they just would have not made this a veneer, if they would have kept the metal off, it would have been fine. But what happens is moisture, when it rains, moisture penetrates through the joint, and then it rots out that upper door trim, and this is what occurs. So after about 8 to 10 years, this whole thing is going to be rotted if they do not address this problem. All right, so I believe we are done. Now, we are done with our time, but anybody wants to stick around and ask any questions? Ray has raised his hand. So if anybody, you're very welcome, gentlemen, and any, ladies and gentlemen, for anything. I appreciate you all for being here.